just a second, we'll connect everybody. Delete this boost down. Okay, let's see if who's online. Okay, I see somebody online already. Thank you for commenting. So the sound and video, okay. X plus minus, I guess it is. We just confirm it. Thanks for likes already. So let's see. Today, maybe let's see how I can structure just this. But today we'll explore the linear algebra, and we'll try to make sense of it. We'll try to make that after this lecture, you will understand why you need linear algebra at all, like where can it be used in practical cases. So it's about matrix multiplications, matrix operations, but we will do this in hopefully very interactive, fun way. At least for me, I think it is. So we will make the computer game. And I will show how the end result looks like. Basically, the whole computer game is based on the matrix multiplications, basically, and vector art. So we'll see if I can somehow run it. Just a second. Show the end result, and then let's go to the previous sessions homeworks just to see the results of what we can learn together. Again, about homeworks, I will have a little bit of discussion. So the full screen, and here, and if I run it, okay, just a second, run. Okay, not okay. So yeah, so the game looks something like this, and you can shoot asteroids. Yeah, only maybe the aspect ratio could be better, something like that. And you can fly around. Oh, and there is even gravity. So basically, maybe you can make it look better actually. So, but okay, it's very hard to shoot asteroid. So that is kind of the idea of the game. But we will try to make it so that it works smoother. But basically, you can change it as you wish. So this will be the game, and and then let's look at the homeworks. So just a second. So regards the homeworks, idea is that again, I don't need homeworks to be done for the sake of the mark. I need them to be done for we can learn together from the homework. So I will have the homework open till the next session, not more. And basically either you do it or not, and then you get points for it. So basically if you do it, then you get points. If you don't do it, you don't get points. If you submit non-working version, it's better than to submit a generated version. Because if you submit just like a code generated version, you don't learn anything from that. So let's see. So what was the homework? So implement object-oriented code using UML, and then also there were the NumPy task. Just a second. So this was the task. Okay, and the UML looked something like this. Copy image, chicks. Where is it? Okay. This is the UML. This was one task. And the other task was the, maybe you can also add that one, was to implement matplotlib. I showed a little bit of it last time, but basically at home you had the opportunity to play around with it more. But we'll see what we get in the homeworks. So this need to implement a function like this and like this. Okay. So that's that. Okay. So I will open a couple of these works just to us together to see them. They also asked to add the some of the screenshots, I guess. Sometimes, yeah, for the next lectures, definitely we'll ask to add screenshots because we will have more and more tasks that are more complex, and I don't want every time to run the whole code. It would be nice to see the end results. So, just a second. I'm just now opening a bunch of works so we can look at them together. So I see that many of these are quite good quality. I mean, like they are not copied from each other, which is nice. So this is nice. Just a second. So I will open also the NumPy task. Just a few samples of that. Okay, we'll look us together what we have there. So just randomly, because there's a lot of submissions, which is very good. Thank you for submitting the tasks. This is. No, I will share. Just a second. The one thing which I also see is that some people submit zip files. Please don't do this. It's if there's not. So I think always there will be just one file, because then it's easier for me just to go through the code with you together if you don't submit zip files. So okay, let's see. So the window capture, PyCharm. Okay, this one. Okay, cool. So yeah. All right, let's actually do the full screen so I can have the proper things. Okay, so this is one sample. If I run it, let's see what we get. Okay, so this is the result. This was the linear. This is the function that was. So there is the function. I think in Python you can actually implement it a little bit different, in NumPy as well. So. Not bad, but so what I see here is 3x, right? So I think you can rewrite it also like this. Well, so second, disable this thing. So just with two of these. So this is also means exponent. Let's see if it works. Yep. Oh, interesting. Why it's different. All right. So there should be 2e, so multiplied by MPE. Okay. Anyway, so okay, it doesn't look much better, but still it works. So so just for you to know, the exponent or the so the power function is two multiplication signs in Python. But that's nothing wrong here. It's just something to bear note. So the Python language is interesting. There's a lot of small details we can explore together. So okay, so this is one. Let's go further. So I will not go through every probably, but we'll look at some. Okay, so there is also the linspace. Okay, there's nice that there is English comments. I talked about this a little bit, that we should not make like Latvian comments in the code. Also, so this is not that good. So please don't make spaghetti scripts where you have something here, then something here. If something fails here, there's no way to debug this. This will be extremely important when we still start complicated mathematics. As soon as I put a breakpoint here, I cannot put a breakpoint in between operations. Try not to write everything in one long line. What else? What else? So the linspace. If somebody didn't know that, also the funny thing that there is no number of elements, but we could add it. So this means it will give me the array of -2 till 2 list, right? And these elements in between, they will be in the number of 100. So if I would add, for example, here 3, then it will be like this. If I add here, let's say 5, then it will be -1, 1, and so on. Clear? So this is kind of nice function as well for the NumPy. NumPy I'll have a lot of nice functions for mathematics. Okay, so this is something you can also add as a comment here. Keep on. So there's another one. Oh, what is this? So if is Scalar. So interesting. When it's not Scalar, what do you mean by that? Not really sure about this, but one thing I am sure, so it is not advised ever to write functions in this way. So even in some programming languages like Pascal, there is a requirement that you always have one input, one output of the function. So you would have something like result, and then you can add some empty array or something, right? And then result will be here, even though I don't understand exactly why you need Scalar check here, but let it be. So if it's a multi-array, right? I mean multi-dimensional. So and then return like this. So from my personal experience, I have seen huge mathematical functions where somebody put return in the middle of function and then spent like 2 weeks debugging this code because like so the other guy didn't explain that somewhere in the middle is return. So it's always for everybody much easier code if there is one function input, one function output. Even though you can do this, especially these returns in middle of functions are very useful if you code in very low code like C language or assembler, for example. But if you code in Python on C#, .NET, Java, then it's not very smart to do returns in between code. But so I advise you not to do this. But still. So here's another one. Seems about right. Oh, right. What is here? So there's also ticks. So a range function. It's actually the same as linspace. So a range is like the linspace, but linspace will give you also fractional parts. So here it will give just the integers, right? So this will be from actually this interesting way how it's written. So there is the start, stop, step, right. Okay, cool. So this will be -2, -1, 0 until the 3 with the step of 1. So NP arrange also gives nice outputs like this. So -2, -1, 0, 1. Okay, and here with this one it will give 0, 50, 100, and so on. So these are nice functions to use as well. Okay, let's move on. So this will be the page 5 in this whiteboard. Okay, so here is another one. Oh, there's some kind of recursion. Very interesting. Run it. What is meant by that? Please select value. Okay. Okay, 3. Okay. What about this recursion? Why do you need recursion here? Max depth. and start. I'm just looking at it. Start and not sure why do you need recursion here. Here, x linspace sinus. Yeah, not sure about what. Yeah.
That it was in the rules of the task that it's optional.
Oh yeah.
I think also for this task.
Let's see. So submit the source code or recursion. Right. I was meant something else by recursion. So this is a little bit nonsensical. Recursion would be more interesting to make this function itself. You know, like if you don't use built-in, for example, like a power function or yeah. So basically, power function is the only one where you could use the recursion. About this one, I don't see the value, but still, okay, that's good, that's good. I appreciate the effort, so no worries. So I think here is somebody tried to made recursion, I can see. Yeah, so this seems about the way how I wanted. Yeah, so this is nice. Good job here. So let's see it further. Okay, so these are all the same. Okay, let me close some of these things. It should be more of the files. Okay, interesting. Just a second, I will open the other files, but I thought I opened them. I don't see them. Just a second. So here I have on Jamboard stuff. I thought I opened them. I don't know where they left. So the UML task. Okay, let's see. Let's try to take some random files. We cannot spend too much time on this, but we'll need to learn something. There's a lot of homeworks, which is very nice. Thank you very much for the effort. So, okay, let's move back to the full screen. Okay, cool. So here's one implementation. Let's look at it. So static object. Okay, let's also open the UML diagram here. Just a second. Where's the UML diagram? Save. Copy image. I will open it somehow. Open. Wait. There, we'll open it in a second. So, okay. Whoa, that's interesting. Again, save image. It's a bit annoying. Open browser. Save. Downloads. Yeah, it will be opened, hopefully. Yes, finally. So, I'll show you just a second. Okay, good. Full screen. Okay, so, yeah, so this is the diagram. Okay. So, static object, the movable object, inherited from that. Where is the static? Yep, game. There is a singleton implementation, seems like. So this is, if you didn't know, in the Python, this is the way how you define static member variables when you don't have any kind of other specific classes, because sometimes you can override this with the data classes, but not here. Okay, so this looks good.
That's what the singleton is.
Yeah, this is the singleton. I think this is quite nice. I don't see like huge issue with this. It's clear. I have seen sometimes people, generate code which is much more complicated, but this seems very nice. Okay, there's one missing, one extra this one, but otherwise nice. Okay, so here with the rockets. Rockets, do we have rocket? Okay, rocket is here. So the one thing which I advise, so there's a couple of things. First of all, this diamond shape means the aggregation, so on. Then the field diamond shape means composition. Aggregation means that I can live without this object, and composition would mean that I cannot live without this object. And of course, player can live without rockets, and game can live without movable objects. And here, just to make it clearer, I advise to always use also some kind of typing here. So this would be, in the latest Python, you actually can use it in this way, I believe. But in the previous Pythons, you would have imported the list from typing library. So if you do this, then then the development environment will check if that is the correct data type. So that would be advisable. But otherwise, I don't see a huge issue with this code. So very nice. Let's look at some other examples and then move on to today's session. I will also look at the chat, so if you write something in chat, I will answer in a second. So not second, a bit later. So static object. This looks interesting. Let's go back. Okay, this might be some student from previous years because we definitely didn't have yet geometry. We will do geometry today. So this one, okay, so here's a little bit of typing. In Python, this is the way how you type functions. This is not bad. So this is very nice that you define what will be the inputs of the types of the inputs of the parameters and outputs. So that is useful. So I can advise you to do this, yes. So this is nice. Otherwise, it seems like that you understand some basic UMLs and object-oriented programming. I don't see huge issues with the code. Again, it seems like that somebody from previous year. Okay, sometimes you write also like this for the void functions, but it's okay. Yeah, it seems about right. Okay, so let's move for today's session. So Jamboard. Okay. So change my notes. Okay, rainbow. Okay. Okay, yeah, right. So what is the first task for me? Okay, let's start by first making the dot product. So the dot product, I will show you just in a few ways, and then we will understand this better. So the dot product is a mathematical operation. So this in Latvian called Scalarais matrices reizinājums, nevis vektoriālais. So dot product is this scalar matrix multiplication, not vectorial matrix multiplication. And you can do the matrix multiplications between vectors and matrices. And we will look step by step, and we'll do something with the hand, and then we'll actually do some computer game stuff. But the main thing to remember and keep this always in mind when we talk about matrix multiplications, this is two-dimensional algorithm. This is not something like, for example, if you have, let's say, like just a multiplication table from 0 till 10, right? Like in first grade, this is something you learn by heart, right? But the matrix multiplications is not something you learn by heart. This is just a two-dimensional algorithm, basically. And why it's two-dimensional? Because basically you have a couple of requirements to do this. So first requirement is that you work with the first input, you work with rows, and with the second input, you work with the columns. So like this, and then the output is defined by the size of something in between. So let's use some color. So here, so this one, this row's size must match the column size, and this will be the output size basically. We will look at this in a second more, but just to keep in mind that. The other thing which we need to see here is that even though this is a vector, in matrix multiplication, I repeat, everything is two-dimensional. So actually what it means is that here what we have, so this is the row. So row is the first thing in the NumPy, and at least in all programming arrays. So this case will be, so row, column, I have 3 columns. So row, I have 1, just don't want to mess up. I think there should be around here something like this, so that there is extra these guys. So, and in this case, if this is a column, so I would probably think that there would be around here another bracket. So this would be something in the programming. Maybe I switched it around, we'll see, but I definitely know that row is the first dimension, column is the second, and if I have more dimensions, it will come in front. So we'll go step by step through this, you will get it. This is nothing out of the ordinary or too complicated. So, okay, so let's build something up. The one way I could do this is using LaTeX. I highly recommend anyone to learn LaTeX. So LaTeX is the way how to write equations using code. And this is used in all sorts of scientific publications as well, often. So this would look like LaTeX editor for me. And we'll try to do something here. So first, you can write this with the hand as well, of course, but now I just will show. So A, 1, 2, 3 here. Then what we have, let's say, B vector. So B vector will be something like this. Chicks. Oh, I don't like that I have a new line, I guess. Yep. So 4, 5, 6. So that's that. 4, 5, 6. Only I don't like it that it's in that way. 4, 5, 6. I think it should be a little bit in different way. Okay, so let's rewrite it. So like I had on the Blackboard basically. So here will be the new lines, chick. Oh, actually, let's do it different way. So this is a B, and so there is a requirement. So actually, we cannot do matrix multiplication here properly because it is not a line here. So what we should have do is to transpose. So, and transpose looks something like this. So it's you will if you don't get it now, don't worry, you will get it very soon. It's not difficult. So transpose will do this. So let's add some spacing here. What was the spacing symbol? I think something like that. Let's see. Does that make spacing? Oh, no, that's not spacing. I forgot the spacing symbol. Oh, yeah, this one is spacing. Okay, so that is then transposed. B transposed. Let me see. Oh. So B transposed. Actually, the A also should be transposed because you cannot do matrix multiplication in that way. So let's transpose A. Chicks. Here, something like that. Okay. This is this. Okay, cool. So this is one thing, and in NumPy this will be super easy. You can just use np transpose and it changes the direction of the vector. And again, the direction of vector is just because there is so there is the two-dimensional array, right? So I can rotate it. So that's that. So let's try to do this this very basic multiplication. Let's do some couple of things step by step. So first, for the matrix operations, and I will show just in a second everything in Python as well. So if you do A plus B, for example, so this is something you cannot do. Basically, it will be error, right? Because the shape is not right. So this is very important in deep learning, in machine learning. This will be super important. It's called the shape, so the form or shape of the matrix. So it's not aligned, and we will do the exact examples which I showed now with the hand, also with the code in a second. You will see how easy it is and how important it is. So, but what you can do is do with the transpose function. So with this one, it should work. So chicks, yeah. And here the result will be, I will show you. So it's easy to calculate, right? So this will be just pairwise, right? So there will be 5 here. So this is 1 plus 4 equals 5, right? And this will be 2 plus 5 equals 7. And this will be 3 plus 6 equals 9, right? So, great. Clear, right? So far, super easy, okay? I cannot do this multiplication if it's not aligned. If it's aligned, then this works very nicely, right? So, and then the result, actually, you never actually write these plus signs inside matrix. You just write something like this. So far, so good. So then let's try to apply the algorithm which I have on the whiteboard for the multiplication of the matrix multiplication, or it's called dot product. So the dot product looks something like this. So we should have the B, I think, no, right. So A, T, if I want to do this in this way. So, and then C dot B, T, and yeah, and this will be this operation. And the transpose is, I'm illustrating transpose only because I want to show you that that basically you always need to make sure that they have the right direction of the matrix. So the number of columns, so the number of rows must, the number of rows must match the columns. And this will be more interesting and more useful when you have more dimensions than one. So, but actually let me arrange a couple of things so this looks more logical. So let's move it here. Okay, so there is whoa. So just a second. There is A transposed, B transposed. And again, I highly recommend to learn the LaTeX equation syntax. It's very useful for mathematics. Okay, good. So far so good. And then what we do the pairwise these multiplications. Just to remind you how it looks like if we go here. So what you do is you take. So you take A1 and multiply it by B1 plus A2 multiplied by B2. So each row element is multiplied by each column element down the road, and it's always add together. So there is just multiplication and addition, and this is a two-dimensional algorithm. You go in a for loop in one dimension and for loop in other dimension. So we'll look at this, how this works. So let's go back here, and you will see why it's super useful for the practical tasks as well. Okay, so this is this. So let's try to do this. So actually, so so this is 1. Oh, there's something not right. So 1 should be like that. Another, so no, AT. So yeah, 1 multiplied by. Okay, let's. I think it's very. It's not visible. So it's. Let's do a little bit different. So let's add here chick like that, and because otherwise I cannot see it well. So let's see, like add something like that. Okay, run. Oh, messed it up somewhere. Okay, this all goes good. This will be good. A, B, T as well. Go on here. Okay, let's see how it looks like now. Okay, good. Now it's more clear. Otherwise, it was a little bit messy. So okay, so 1 multiplied by 4, plus let's say 2 multiplied by 5 plus 3 multiplied by 6 equals. So this will be 4 plus 10 plus 18. I guess so. I have no bugs here, hopefully. So 28, 32. I think it should be like that, if I'm not mistaken. So let's add here a new line. Okay, like that. Okay, cool. So I will add this to the Jamboard, and then let's try to do this in the Python. So if you could make a new Python file, we could play around with this and then do more complicated stuff. So I will add this to, okay, copy JPEG. Okay, cool, JPEG works. So I'm adding this to the Jamboard as well, I mean the Whiteboard. Okay, great. So we'll share you the code as well. So let's create some new file, 2.1 live.
Sorry, why did we
Yep.
transpose?
Sorry?
Why did we have to transpose?
Transpose, yes, this is important. So you will see that's more and more. Just don't worry if it's not like immediately understandable, but the transpose is very important because basically the two-dimensional algorithm goes, so basically here is a for loop, it goes in this direction, and then the for loop goes in that direction. And if it's not aligned correctly, then you cannot do this operation properly. So it's you will see that one for loop goes, runs out of the, so it ends, and the other one keeps going, and how you can then multiply it, right? So you will see this in a second more. So, but this is right question. This is correct. We will explore this, and with two-dimensional stuff as well, no worries. This is important to understand. This is the basis of all deep learning, machine learning algorithms, and this will also be very nice for our game. So if you go to the Python, oh, right, okay, Python. So let's do the same thing with NumPy. So import NumPy as MP. So this is like the standard way how you usually do this. I will do this code and then look in the comments in YouTube just a second. So, okay. So let's look at my stuff here. So we could actually write exactly the same thing here. Okay, let's actually try to make everything in 2 dimensions so there is no confusion. So A will be MP array, and let's try to make it exactly like it is in the example. So so it means that first there should be something like this, chicks. So and this will be 1, 2, 3, and then the B will be aligned in a different way. So I believe it will be like this, 1, 2, 3. Again, so we will already start seeing some very interesting patterns. So if you look at a shape, so this is the this will give the tuple of the shape of one and tuple of the shape of other. If I run it, we will see that one is the 3, 1. So again, I remember two-dimensional algorithm. So this is a two-dimensional algorithm, and even though I don't want to give you too much information now, but it can have more dimensions, but it always will be two-dimensional algorithm. Even if I have 2 dimensions, it will be executed only on the last 2 dimensions. So, and also, this is something to note. For example, I have two vectors or two matrices here. Then if I change the shape, it do not change the data. So even if I add here another dimension like this, don't do this now, but if I do this, it will change the shape, but it will not change the contents of data. So this is again critical, because in deep learning algorithms and machine learning algorithms, we change the shapes all the time. Like we try to, like we rotate it, we like, for example, we also can flatten it, we can rearrange it in different order, but it never changes the data. So it's sometimes when you look at from the programming perspective, okay, it changes the sizes and so on, but data stays the same. This is very important to understand. So let's keep digging. So if I'm replacing it back as it was, like in my LaTeX equations, now if we can try to do a couple of these examples. So first, let's say A transpose here, A transpose like this, right? And B transpose, B transpose. And if I would look at the shape, you will see that it is just the same data, you know, transposed. So shape, and this dot shape is very important. Dot shape we will use a lot in our endeavors. So if I run it again, so okay, it transposed. Great. So, and if I look at some of the things which we did, so what we did A plus B transposed, yeah, and we can actually, what we could do, we could print out the result, or we could save it somewhere, so run, and we see 2, 4, 6, and it is this different from what I wrote. Why it is different? So that's funny. So BT 4, 5, 6. Maybe right, I know why it's different. I accidentally wrote the wrong numbers here. So here should be 4, 5, 6. Nobody helped me here. Maybe in the YouTube. Let me check. I was not paying attention for YouTube for a while. Okay, thanks for 5 likes. So there's a 4, 5, 6. Okay, and then this is 5, 7, 9. So just A plus BT. And if let's do experiment. If I do this with A plus B, hopefully it will fail. Oh, it didn't fail. So there is something called broadcasting in NumPy. So we tried to do some magic here, but it normally should not work. So, but basically, this is the way how it normally should work. So, so this is so the broadcasting means it just copies multiple times the same thing, but we don't care about that. So A plus B, this is normal mathematics, right? So that's that. Then let's try this dot product thing. So dot product thing. So this is also built in NumPy. So np dot, and we'll also try with multiple ways, see what happens, right? And then we will try to do this more manually with complex matrix, and this will be interesting. So AT, BT. Okay, so now we have, this is the output actually. So 32 with two brackets around it. So, and how this happens is because the output dimensions come from these places where it matches together. We will see this more in a second. So, but basically this is correct. If I try to do this with some other variants, it will also work, but it will work very differently. It will try to make large matrices. So, okay, but let's do step by step. So this is the same code what we did with hand, and let's try to now make more complex matrix multiplications, and then implement in the game, and then understand why it's useful. So okay, so I'm adding this to the Jamboard, to Whiteboard. Let's return back to the LaTeX. Okay, so cool. And in the LaTeX, I have more ideas what we could do. Let's see. So I have that one. We could actually change this shapes. That's one option. So do we have the correct order? Just a second, looking at, because if you do it in the wrong order, it still works. So, but it will give you different way. Okay, so okay, I have idea. So I have idea. So B, A. Let's try to do this equation. So let's try to do this equation. Chicks. Okay, cool. So I will copy what I had before, and we'll copy new equation. Okay. Oh, it's not copying. Why? Paste. Okay, cool. Run. Okay, great. So yeah. So let's try to do this one. So the can anyone give me the answer of this one in the chat as well? Maybe somebody in chat can give me answer of this one. Yeah, think about it a little bit, and if you're here in the person, you can tell me, or what do you think?
It shouldn't work because the number of
Yep.
rows is not matching the number of columns.
Okay, that's I like that you tinker along. I don't see anyone in the chat writing yet. Think about in the chat as well, but let's start implementing. So if I start to multiply 1 by 1 plus 2 by 2 plus 3 by 3 plus 4 by what? Nothing there, right? So this is what I mean by this is two-dimensional algorithm, and the dimensions must match. If you have situation like this, you have error, and we will try maybe this in Python as well and see if we can get error in Python as well. So let's see if I'm adding this on the Jamboard. Not Jamboard, Whiteboard. I always. Okay, let's go here, and if I modify this code a little bit, we'll see if it fails. So so I have here. Oh, if I just will add here maybe extra dimension 4, run. Yep. Right. First of all, it already failed here, but it should fail also in the dot product. Yeah. So it says dot product not possible, not aligned. So this is what I mean by that. Okay. So this is great. So we're starting to understand a couple of basics, but we need to go more deeper. So okay. Let's look more examples. So go back here to Jamboard, and I will copy a couple of visual examples. So what happens if we have, let's say, a little bit more complex matrix? So here, let me copy some of the example. Copy image. So if I have not just so the previous examples which I give you here, so these are actually vectors, but they are represented as two-dimensional matrix, but they are vectors basically. So it just the rotation is determined by the extra dimension. But if we look at like proper matrix, it looks something like this. And if you see here the R, rows and columns, these are also vectors. And then if you look at each of these separate values here, so this is actually a dot product between two vectors, okay? And then starts to happen really interesting things now starts to happen. So the couple of really interesting things are following. So, so this is 3 columns, and here is also 3 columns. So this dimension is eliminated. So if you look at this, so this is eliminated or removed. So this dimension, which is 3-dimensional stuff, is now disappears. But what we have here is, so this is some of the matrix properties, and these are fundamentally very cool and very powerful. So see, this one is the same as the output dimension, and the other one will be the same as the column dimension for output, okay? So, and what actually this means is that if we do this in Python, and we'll try to do this in Python and by hand, and we'll make sure that this is very nicely working. So this will be, in this case, 2 by 3, the shape, yeah? dot product by 3 by 4 shape, and the output is 2 by 4 shape. Yeah. So this is not the actual numbers, but this is just the shapes. So shapes. Yeah. And the shapes are very important because we will start talking about something that is called projections. So we can project, you could think of projection as the shadow. So from the light shadow where it splits, and this is the same idea with matrix. You can project from three-dimensional space. So I have three-dimensional object pointing at the light, and on here I see two-dimensional picture. You understand? Like if I hold out some kind of item which is hopefully not transparent, right? With the light, and the light hits it, and then the shadow is on my table, and this will be two-dimensional. So this is one of the very cool properties which we can get with the matrix, and we will also do this with the game. So let's try to maybe have some example with this in LaTeX as well, and then with the code, and then try to implement this algorithm yourself. So let's see. So LaTeX. If any questions, write in the chat. We'll do very slowly, step by step, so everybody gets it, because it's not really that complicated, but we don't want to mess it up. So let me find, all right, I have another nice picture. Let me share another nice picture. I found this early morning. So another nice picture is something like this. So here we can look at what is the output. So, and there's one more very interesting thing to look here, because in the previous example we see the dimensionality example, right, that the output of dimensions are changing. So the input dimensions along one axis must match, but the output dimensions will change. By the way, if this is 4 by 4 dot by 4 by 4, then it will not change, right? But if it's different, then it will change. And the other one here is something else. So in this case, we see something other interesting thing. So here you see that this output is just 1 by 1 here, right? Like in our original example. And this is because here we have 1. This is eliminated, and right. So sorry. So this is eliminated. So this is eliminated, and this is eliminated, and the outputs becomes here the 1, right? So here's the 1, the green color just. So this is eliminated, and the output becomes here is 1 chicks, and actually here, and the other one is this one, right, like this. So, and this is 1 by 1. And then what you do here's in the top actually the mathematical equation. Basically, you do this dot product between each of these vectors, and your output is always 1 by 1. Even though there is also one thing to keep in mind, and we will talk about this later more, is you can have extra dimensions around it. Like here you can have, let's say, hundreds of dimensions more, but they will be ignored. Basically, all of the calculations will happen in last 2 dimensions. Basically, these brackets will stay the same. If I add here extra bracket here, okay, I add here extra bracket, extra bracket, extra bracket. The same extra bracket will be here in the output, but the algorithm itself works in the inside in these 2 dimensions. So that's very nice. So if we go back to the previous example where it was visually with the numbers, and then let's try to do this in LaTeX. Just a second, I will pull over some example. There is some LaTeX code. There must be some. If not, I will write some code. Okay, let me write some code. Okay, let's just write some code ourselves. Okay, so cool. So this will be, let's make this work. So so I have so 4 dimensions, and let's make it something along this line. So here will be another one. So the best way how to separate it would be something like this. Well, Sorry, I'm not showing something. Okay, sorry. Chicks, thank you. So there will be 2. I'm just rewrite a little bit so we can play around with this a little bit. So chicks 3, and here will be 4, 5. Hopefully this is what I have. Run. Okay, so this is this is like that. This is like that. And we will eliminate columns. So let's try to make something interesting here. So chicks 4. And in order for this to work, we need to have another row here, something like this. Okay, cool. Well, except let's try to make with some numbers which are not the same. 6, 7, 8, 9. Okay, don't want them to be too long actually. It can be actually minus numbers as well. Okay, so let's add here -1, -2, -3, -4, like that. Okay, oh, it's not looking nice. Okay, let's do some other 10, 11, 12, 13. Hopefully now it will look nice. Run. No, I don't like it. Just a second. I know how to make this looking nice. Just a second. So B matrix. They should have tried to split it in. Okay. Let's not waste time on this. I will just use 1, 2, 3, 4. I think there was something called a line to make sure that this is a line. Okay, cool. So we have 3. So we have 3 by 2 shape and 2 by 4 shape, and this 2-dimensional stuff will be eliminated. So what we can do first, and this is very important now to observe, because in a moment you will try to implement this algorithm yourself, is that basically here we need to make sure that we have we create a template for the output. So template for the output will be something like this. So the template for output will be let's say Z1. So this will be just a second, let me think about it. So it's easy to mess it up. I don't want to mess it up. So the first one is 3-dimensional stuff. So here will be Z1, Z2, Z3. With the programming language, it's easier. So this is a 3-dimensional, and then it should be 4-dimensional in my opinion. So here will be Z something, Z4, Z5, Z6, and then I need to repeat this stuff again. Z7, Z8, Z9, so this is 3, then I need to have more, Z10, Z11, and Z12. Great, so this will be the template, and when you just a second, when you program the same thing yourself, this is also to keep in mind that it is advisable to make the templates basically for the output. So you already will know what is the output size of the shape, and then let's make a template. So like that. Great. So we have a template and everything lining up nicely. And now what we do is we calculate each of these z's, and each z's to calculate, it's easy. So for example, z1 equals, so this will be the row. So this will be the row 1, 2, so multiplied by 6, 1, I believe. Yep, so this will be 1 multiplied by 6 plus 2 multiplied by 1. So if you could do this your own, try to do, I don't ask you to do the whole matrix, but try to do some yourself, so you get used to it a little bit. So this is 6 plus, so this is 8. So like that. And then what actually it means is I can start plugging them in this equation. So if I start plugging them in, it means that here I write 8, right? Like this. And then I need to do the same for every single of the 12 elements, and then basically I would end up with the end result. And we will do this quickly also in the NumPy and make sure that this works. So, but try to do some elements by hand so you get used to this idea of multiplying and summing. So just a second, go to Jamboard, Whiteboard, need to rename it. We'll look at in the chat as well in a second, just to make sure that everybody is on the same page. So again, let's color some things here. So Z1, and how did I manage to get this? I did this matrix operation by using this row, and here is 1 and 2, and using this column, and 6 and 1, right? So you can do this manually yourself, right? Do you understand this, or there is problem still? Is it okay? Like for example, well, what is the value for Z4? Okay, let's do it this way. Let's not ask every single example, but just one by one. So think of the answer for Z4. I will ask in the chat as well. So what is Z4 in the chat? Please try to do this manually. And let's say Z9 as well. Somebody could calculate, and I will tell me. I will write it down and then check if that's correct. Okay. So what is Z4 and Z9? You need to paper or some you know, write a little bit of numbers, because I don't. Maybe you can do this in head as well. It's not too difficult. Z4 and Z9, let's say. Okay, let's write it actually in the LaTeX. And I wrote also in the chat question, so let's wait for somebody else to answer there. Okay, let's move to here, and I will add his Z4 and Z9, and I will make it so everything is visible. Just a second. So chick, okay, like that. And let's remove this one and run it again. Oh, where did I left? Oh, Z4. What are the answers? Do you know? No ideas?
I don't know which elements I could do.
You don't understand what I'm asking? So,
No, yeah.
so Z4 and Z9. So, what are the answers for those elements?
I mean, I'm not sure.
So, okay, so Z4 and so this is Z1. This is how you calculate Z1. You have vector here, and then you do the dot product, the same operation which I showed you just before. And now my question is for Z4 and Z9. So the same operation needs to be repeated for those cells in the result matrix. So the Z value is actually template, okay? Just a template. For you will do the same in programming code. You will have empty matrix, and then you use the for loop to find the right cell and place the value inside. So my question is for Z4 and Z9. I just want you to calculate, and then we will check. I'm also asking. Oh, in the chat I see somebody answered Z4 11 and Z9 47. Any other ideas? Let's double check if this is correct. Can you verify this is correct or not correct?
No, I don't understand.
You don't understand.
Which elements from A and B
Okay, okay. Let's keep going slowly. So let's go here back. So in the chat, somebody understood. So somebody wrote already. But let's go again step by step. So here, so the okay. Let's say Z4. Yeah. So what is Z4? So, and let's use another colors here. Hopefully I will have enough colors. So the Z4 means, so I'm located here in the, so in this, it is here, the second one. Okay, so this is cool. So this means that I will take, well, why the color is not working? So this will mean that this is the Z4 is located here, And this means that it is located on the first row. So it means that I need to take this part, and then it's located on the second column. I need to take this part. Got it?
Yeah, I guess.
Great, great, great. I'm not judging you. It is need to get used to it, and basically this is something to understand. So here, if we try this one with other color, so let's use blue color. So Z9 is located actually in different location. Z9 is located here, and this means that we are now targeting this line, and we are targeting this line. Okay? Is it clearer now?
It's good.
Yeah, great. Try to calculate it, and then we'll see if this is right. Only one person in the live chat answered, which I hope somebody else will also calculate it. And then let's verify if we understand this. And yeah, meanwhile, while you do this, I will open the new task, which will be the implementation in Python, this two-dimensional algorithm of dot product, and then we will use the same algorithm for making the game. So let me find. Okay, this one is here. Good. So task, and those of you who understood already can go and start implementing that task. So this will be 2.2 task. Just a second. So I need to change a little bit of. Oh. You managed to calculate? Okay, great, excellent. So this is something we need to practice a little bit, and then it will be great. Okay, so I am adding 2.2 task. Save and return to course. Okay, so I think it is added. It is added to the Moodle, my YellowRobot Moodle. Okay, so anyone else in the chat? Okay, great. Somebody, so 3 people agrees. That is excellent. And do you agree that this is 11 and 47? Yeah? So let's see if this is right. So here, this will be 1 multiplied by 7 plus 2 multiplied by 2, I guess. And here it's 11. And this one will be 4 multiplied by 8 plus 5 multiplied by 3. And this one first is so 15. So 4 by 8 is 32 plus 15 is 47. Great. Excellent. So this is that. Yep. And then I opened just a new task, and let's go to that task. So please, in the Moodle, take the task, and I will show you how it looks like. So let me write. So I'm just opening it, showing you in a second. Okay, great. So this is the first task, and we will implement the dot product function. So here in the bottom part you see mp.c, and here is the dot of your own product. And basically let me explain a couple of things. There's nothing magical here. So the first thing is at least 2 dimensions. So what it does, if there is less than 2 dimensions, it adds the row dimension around it. That's just it. It is the this kind of simple abstraction, because people, when they think about vectors, they think something like this. So this is a vector, but actually everything is matrix. There is no vector actually in these calculations. So it tries to make it like that. That's it. So that's that, but normally you would not pass it in that way. And then here the flatten means that you remove that extra dimension. So, and what else? So here is the A, and here is the B, and then here is C and D, and then there is the, in the bottom part, the calculations. If I run it, I see that, for example, the first one is my own, and the second one is made by NumPy, right? And the NumPy gives me these values and these values, and these should match between each other. And here's even more interesting things, I think so. So let's look at this a little bit more. So here is C. C is this guy, and B is this one. And notice here, this is really cool. And this is this projection thing, which I said 3-dimensional objects can be projected with the light on 2-dimensional surface. So if you look here, what happens actually is that the C shape is 3, like that, right? And it is actually then produced in 1, 3 like that, but basically you can look at this tree, right? And then when you do the dot product with the, so this is with the B, I guess, yeah, so there is a 2 by 3. You end up having 2-dimensional vector, see? So 3-dimensional object is now projected on 2-dimensional vector. So, and this matrix in between, this 2 by 3, this is kind of, you can think of formula how to project from 3 dimensions on 2 dimensions. Basically, this is how to look at this, okay? This matrix is kind of like a formula how to predict, and this is based on the numbers inside there, right? So every time when we arrange matrix with different numbers, we will have different formula, so to say. But at this moment, we're not talking yet about the formulas themselves. We're talking just about the implementation here. And if we add here like some breakpoint, please try to implement this, and the remote people as well. And if nobody will be able, then I will show how to do this, but I will start showing you ahead. So if I add here a breakpoint and run this code with this bug, yep, so I get here the stopping, and I have some of the things. So X is the first one, X is the 1 row, right? And this is the 3 rows, and the column, and the Y is 2 columns. And here the product is this thing which I produce as an output. One thing I advise maybe is for us to make it easier to understand, we could work not by just projection method, but by very simple matrices. So I believe we can also do dot product in between A and B as well. So let's see if I write here print A and B. So this is 2 dimensions, 2 dimensions. I believe it should work. So if I run it, yep. So the output is 2 by 2 here. If we look at here, let's make it clearer. So let's print it in 2 lines. I highly advise to test this algorithm using this method by A by 2. So A by B. So this is the correct output, and this is your output right now. And how to do this? So basically, if I add here a breakpoint, I now have really nice situation where I have two different matrices, X and Y. And if we look at here below, so this is the X and this is the Y, right? So this is the X and this is the Y. And then we produce the output. The output we definitely know. I already give you the templates here. This will be 100% the same output, right? This is given. So how to approach this? So first, what we want to do is we want to go through the rows. So for E in range of output rows. So output rows will be the same as input rows, okay? So, and then for J in range of the y columns, or the second variable columns, which will be also the output columns. In this case, basically what we have here is 2 by 3. So again, so the x in this case is 2 by 3, and the other one is, I think it was 3 by 2, and then the output will definitely must be 2 by 2. Nothing else will be there, just 2 by 2 output. And now what you do is you go in each cell of the product and calculate this very simple algorithm. You can use more for loops, you can do it whatever you want, but calculate for each of the cell here the output. Is it clear what needs to be done here, or it's too complicated, you don't understand? So let's ask also the group in the YouTube, maybe somebody. So are you able to attempt this, or should I show how to do this right away? Because this is not difficult. We did this by hand just a minute ago, and now it's need to be done automatically using the Python code. So those here, please try to do this. Like you cannot lose anything. Just try to think about it and try to implementing it. If it's not works, I will just show how to do this correctly. And remote people, please also try to do this, and ask, like if somebody will attempt to do this, please write in the chat so I know to wait. If nobody is able to attempt this, then I will start showing this basically. It is literally a couple of lines of code. Remember that we can access elements in Python by having, so if somebody has problems accessing elements, so this would be something like this. So product E, J, it means selecting the row and column, and here I need to put in the right calculation. And to have this right calculation, you probably have multiple options. You can have more for loops there, because remember there is summation, right? Or you can have some other Python tricks, but we can do it very simple way as well. Those people who are good at Python can do this very easily, but those who are not as good can maybe make a for loop there, another third for loop. So it's not out of this role. So try to do this. Okay, need to refresh memory very slow. Okay, somebody says there will be very slow. Try to do this basically. Again, so I can maybe show just visually what we need to do here. Try to implement this. So let's see. So if I add here a breakpoint, so, and you can do with breakpoints, you can also work with this. So I say the 0, 0, right? So what we have here is so 0, 0. So we need to first look at row 0. So here's the x, yeah, the first input, row 0. So row 0 in this case is so row 0 in x. So in x looks like 0, 1, 1. Oh, right, 1, 3, 6. Okay, great. And then I need to have y column 0. And this looks like this. So this is 1, 5, 6, right? And then what I need to do for the product, so the product here basically must be, so if I'm looking at 0, 0, it must be 1 multiplied by 1 plus 3 multiplied by 5 plus 6 multiplied by 6. Is it clear what needs to be done, right? So here you can visually see it. So you have one matrix, another matrix. You just need to make it automatic so that it works with any kind of matrix, not with just this one matrix. But this, as I say, this is two-dimensional algorithm, and I cannot stress this enough. because I know students who try to learn deep learning and machine learning and they don't get it for a very long time, that this is two-dimensional algorithm, not some kind of magic operation. So, and this is very important actually. So if you could try to attempt this, let's see if somebody else says in the chat, will somebody attempt this? Plus, minus, please give me plus, minus. But I know that when I do this course with some AI talent programs, which are even not the masters, they are able to do this. Like even like high schoolers can do this. This is not crazy difficult to do. So I don't see yet response from live stream. Please try to do. I will come around and try to help you if something is not working. Also, we cannot spend super much time. Definitely, we will go a little bit past 11 today, but we will not do this like super long. So, okay, nobody responds in the live. So basically, what you need to do if you want to do this with for loop, you need to select the right column, select the right row, and then go with, like, let's say x and y variable, and select all the items and sum them together, multiply and sum them together, right? It's not crazy difficult. Mēģināt, ja? Jā, nu vienkārši pamats vajag padomāt par šo, jo nu, tas tomēr ir tāds fundamentāls pamats tam visam. Nobody responds in the live stream. Okay, I will check if somebody submits the code in the Moodle. We saw somebody who submitted the code. Not yet. I'll give a few moments, try. Okay, I will start writing something, and then I will show in multiple ways how we can do it. So here is the, let's say, the accumulator value result, and we could what we could do, we could have it here as the output, and I will do this the dummiest way possible, and then try to show how you can do it in a smarter way. So for so this, in this case, what we need to go is the row. So let's say x value in range of x columns, because I will need to go across columns. Okay, I don't have columns registered here, but I can do this. X columns here like that. And then I need to also go through the rows for the other part, y rows. And then I need to multiply them each together and sum. So I would write res plus this and the x, x. So now I go through the I row with the x column multiplied by y, j row with the y row with the j column. Really hope that this is correct. We'll see. So if I'm running this, actually this is the whole answer, I believe, but let's make it more simpler. Oh, right, it's not correct. No worries, we can fix this. But this is in the right direction, definitely. So okay, why it's not correct, we'll see in a second. So let me debug this a little bit. There must be some small mistake. Somebody sees it, can help. So I need to go I need to go through the I, every element in I. This is correct. I need to go, but first of all, this is already correct because otherwise it would fail. If I not have the right order, it will just have error. So, but there is some bug here. So then Y goes through these columns. This is Y rows with the J. Seems about right, but something is not right. Let's see. What is not right? Because it must match this. Why I'm saying that this is not right, because this is NumPy result and this is my result. It must match them together. And I'm just right now writing it the most simplest way possible, and that's why I'm not sure about the code completely. So I will quickly find the reason. So the Y, we will go by the Y row. Okay, the easiest way is just to debug, I guess. Somebody maybe will help me in the live session. Nobody wants to help me. Okay. Did you find the bug? No bug? Okay, let's see. So the X, this is the X. So this should be, okay, let's double check also if my calculation is correct. So chicks, there should be 52. Yes, 52 I remember was correct. So this should be 136, 136, 136. Okay, great. And here the X first ones. So it should be 136. So this is 1. This is correct. The second one, again 1. This is not correct. Oh no, right, it is correct because we are in the Y side. So 1, 5, 6 we need to have, okay. All right, I think because there's these two for loops, they are repeating the same thing multiple times. I believe this is the thing, yes. Because I always write this in a completely different way. I just wanted to try this time different way. Okay, so we'll have X. Okay, I understand where is the bug. I completely understand where is the bug. I'm repeating the same operation multiple times, which is not what we need. And so for the first one, we need to go from X. I'm going ahead. This is great. This is great. With the Y, I should not do this in that way. Okay. Yeah, you can try to fix this code, and then I will also fix this in a second. And also, I will show how to do this much easier, right? Yep.
Online, then you have Y.shape and X.shape.
Oh yeah, somewhere is a bug.
The X columns.
X columns.
Equals.
All right. Thank you very much. And there's also yes. But I don't think this will. Yeah, this is one bug. Great, we fixed one. That is excellent. Thank you very much. The other bug is that we are repeating all the time the same operation, which is we should not repeat the same operation. So just a second, I'll fix that. There must be a little bit different type of for loop. There must be, I believe we should shift the Y values. That's not too difficult to do. So, okay, actually I know where the problem is. So we could rewrite it a little bit. So I'm going through the columns. All right. Okay. So the best way. So the best way would be to use the dimension which will be destroyed. In this case, the dimension which will be destroyed is 3, because if you look at this, it's the same size here, right? So the same size. So what we could use is in the range of the dimension which we will destroy. In this case, this is x columns dimension. And then let's do here k and k. So now it will be correct. So actually great that we did this with for loop. I normally do this in completely different way. I will show you the different way as well. Okay, and now, oh, right, something did not match. J out of the bones almost correctly. Something is not correct. So let me see. So I have that dimension. This is great. So K, J. Something is wrong. It must be the same. Just a second, we will fix this. So X shape is correct. Correct. Columns. So let's write it in this way. Rows, columns, correct. Okay, I need to put a breakpoint, I guess. But this starts to look much better. Previously, my bug was that basically I was adding the same thing many times. Now it's this illustrates perfectly the idea that we will destroy this third dimension in between. So let's see. So x first element. So this is 1, great, and the other one. Okay, let's actually write it in. The console is great here as well. So okay, so this is 1 by 1, excellent. Next loop. This is 3 by 5, excellent. Then the next loop. 6 by 6, also very good. And the column size is 3, so it seems also very good. Maybe the error happens somewhere later, I don't know. Like, let's see, run. Yeah, it actually works here. Seems very nice. Maybe it's happened somewhere later. So let's see if I add here a breakpoint. Okay, it works. Okay, great. So this algorithm works. This is the correct way how to calculate the dot product. But then later it fails probably because some other reason. Let's see. So here, so this works. This works. And the last one didn't work. B by D. B, D. So the last one, I guess something is not right with the dimensions. So let's see. So X shape, Y shape. So this is 3, 2. I believe this should be transposed. So the dimension 2 is which I wanted to remove. Let's see if I run it again. Oh, it still doesn't work. Okay, I'm not sure about that, but basically it works in first 2 examples, and the third one is probably because it needs to be rotated, transposed. So this is the algorithm, super simple. The idea is that we remove this middle dimension. Actually, I like this comment here, because we remove this 3-dimensional stuff here and leave this 2 by 2. So, but this can be done even more simpler in Python. In Python, you can do this in a more simpler way, because actually this is the way how I usually do it, and that's why I struggled a little bit to make sure that this works. So the easy way how to do this is this. So I can use MP sum, so this means summation, and then I can use X and select E, and this means select the whole column basically. So this is like in Excel, selecting the column basically from the row. Yeah, so this will be the selecting, no wait, this is selecting the whole row, sorry. So selecting the whole row and multiplying this by selecting column. The selecting column looks like this. And if we add the breakpoints, we can actually look at these equations. So, and now it's super simple actually. And if I run it, it should work. Yep, it works. And let's try it if this strange equation at the end works. And that also works. But the last one works a little bit different. I believe that this is because numpy dot function works a little bit different. But yeah, so, and if I add a breakpoint here, I just want to illustrate a little bit what it means here. So I add a breakpoint, and if you look at x, so this is the x, yeah, here on the top corner. And if I'm now selecting, let's say, some area, so the first row, I believe this will be. So I have the first row, the second row. See, I can select it with this nice way, with the colon sign. And I can do the same for the rows. Okay. Even though if you're not feeling too confident about these equations, that you will become confident eventually. It's just a normal way how to process this information, because normally in the linear algebra in school, you don't learn about practical applications, why this matters. And I was starting to give you some practical applications like the projection of 3D object to the 2D space, but this will be very clear just in a second with other examples. So, and today we'll definitely go a little bit past 11, but not too much. So, okay, so this I'm adding to the whiteboard. And let's move to the actual computer game example. So the computer game example, I will open new template. So I need to go back to my course, add the activity, to boost new template. 2.3. Implement the change of the angle for the spaceship. So we will have this spaceship. Just a second. So I'm added 2.3 task. Just a second. I just realized that I'm missing something there. Meanwhile, you can look at that previous code, but it's nothing crazy. So just a second. Just look at some example. I don't want to send you wrong code. Okay, great. This is the latest code. And is it? Yeah, this is no 2.14. Okay, this is not latest code. Compress. Share. Okay, just a second. Okay, upload completed. Great. Okay, added. So the task 2.3 is added in the Moodle, and this looks something like. Let me show you. Delete this one and copy this one. Okay, great. So this is how the code looks like. We'll explain you. So this will use matplotlib, which is this library for drawing graphs to draw a computer game. And we also have all sorts of cool templates here. We have like rotation matrix template, translation matrix template, dot product template, where actually in this part we could just copy our code, what we just did, and this would work anyways. So we also have these vector operations. Maybe we could add this later as a task. And then we have object-oriented static object. The drawing functions, we'll go through that as a little bit. Planet, movable object. Did you manage to get the template? Yeah, great. Asteroid, rocket, player, and player. Here we have generate geometry for the player. If you try to run this thing now, I believe it will not have nothing visually visible. We'll see. So if I write here, a full screen run. Okay, so now it's just a black screen. Yeah, if I press escape, I go out of this. And now we could actually start generating here the in the player class, the player itself. So it should have X and Y coordinates. So if we start by, let's say, -1, 0 till, let's say, 0, 1. And then, so this will be spaceship, just a triangle. So 1, 1. And -1, 0. So this should make a spaceship. If I run it again, yeah, see, I have a spaceship here. It is quite wide. We could actually make it as we want. We could have 0.5 here, or later use the scaling function to change this. So something like this. Then now it will look a little bit better, I believe. Yeah, so now there's this spaceship here, right? So you can add this. So the geometry here. And then also what we want is that with the keyboards we can change the angle, rotate the spaceship around. And how to do this? We will use the same dot product and matrix multiplication to do this. So, and then later we will use matrix multiplication in chains, which is even more cooler, which is the way how this must be used. So this is geometry part, and you can add these geometries to all of the objects in this small computer game template. You can add the geometry for planets, rockets, for the asteroids, and so on. It is manually added like this. I believe it's not super complicated. It means like the point on left, point on top, point on right, back to point on left, right? Just like that. So that is that. If we go down a little bit to the game part. By the way, I added this part to the whiteboard. If somebody did not manage to write this. And then if you go down here, there is the right, left buttons, right? Key press right, left, and then there is an angle. An angle is changing. But the one thing which we don't see is the angle visually. I would like to see it visually. So here's the plot. So this is the main game loop, okay? And here is the score, speed, position, but there is no angle. Let's add angle as well. Angle. Like that, okay? Oh, player is not available. That's interesting. Oh, right, we need to have get instance. This is a singleton. Okay, if you add player angle here as well, then it should appear already. So I'll take it to the Jamboard, slide number 15. And now if I run it, how it looks like this. And if I press button, see -35 plus, and you can press with arrows, right? So this is what I want you to create at this moment, and then we will add just in a second the rotation matrix itself. I will immediately open the next task already. So the next task will be implement the, oh right, it's already in this task, sorry. So in this task it says that we need to implement rotation matrix, and this looks like this. Just a second. So this was the last code I wrote. If you go into the whiteboard, you see this is the first code, this is the second code, right? And then it says this implement rotation matrix, and what it actually does here, which is really cool. So you can answer me here on, so if it's like So this is a three-dimensional vector position of the spaceship with three-dimensional matrix comes out the three-dimensional output. Okay? So because it's 3 by 3 and that's a 3, then it comes 3 as well out, right? So this is what we need. And in reality, basically, you can have two-dimensional stuff in three-dimensional vector as well. If you add here in the last one a 0, or in some other operations, it's better to have here 1. But this is what we actually want. So, and this will be the, so what we actually do here. So let me explain. So this is our spaceship. We have actually 4 vectors or 3 vectors here. So this is 1, 2, 3, 4 again when we go back here. And what we do, we apply this rotation matrix using the dot product to each of this vector and achieve that it will be rotated like this. So I will apply it to each of this and let's say rotate by 45 degrees. Do you understand it there? So this is really the main reason why you have the dot product and matrix operations. You will have unique formulas that will be placed in these numbers, right? And when you apply these formulas to the data points, it will produce these projections. In this case, the projection achieves the rotation. In other places, you can have all sorts of crazy, interesting things what you can do with data. You can bring, for example, practically what you will have in the next sessions. You will have, let's say, some kind of biometric measurements, like let's say the heart rate, all sorts of data. Like you will have not three-dimensional vector, but there will be 100 measurements. Okay. And now you will have this matrix that will be able to plot these 100 measurements in two-dimensional space, for example. And then you will see this person in here in this two-dimensional space is the healthy person, and here is the sick person, for example. And this will be really powerful. So this is the very practical application. Okay, I really hope that I'm getting the point along to you, but I'm really trying. So if any questions in the YouTube chat, you can write as well, but let's try to do this operation. So if we go up here, so here should be the matrix rotation, yeah? And identity matrix is also something so the identity matrix means that if I do the dot product with identity matrix, it will not change. So let me show you what I mean by that. And identity matrix is actually cool. You can use the inverse of identity matrix and so on. That's also very useful, but we will talk about this later. So copy image here. So see, this is not my identity matrix. So just a second. Identity matrix will be here. Just a second, it's coming. Okay, cool. So identity matrices looks like that. So they are just traces of ones. Okay. So it's nothing complicated. It's just traces of ones. And what it actually means here, imagine if we do the dot product with identity matrix. So let's see. So this one, yeah. So this with this thing. So after I do the dot product, I will get the same triangle out. Okay. So that's the idea. So, but then the identity matrices are very powerful as well, because you can imagine if you do the inverse, or it means one divided by this, you can check, if, for example, if this is a correct matrix or not correct matrix. But let's do that later. Basically, in this case, this is super useful template for any kind of matrix because it doesn't change it. And that's why I already have it placed in the code, because then it's easy to change. So if we go here, the rotation matrix is by default identity. We need to change it to MP array and start building matrix here. So on how to build this matrix, this is again very easy. So we use the formula, the template which I gave you. So what we could use here is the theta, let's say theta cosinus, or just t cos, and this will be MP. So if this is degrees, we need to change it to radians, I believe. So MP cosinus, MP radians degrees. I hope that this should be something like that. We'll double check. Yeah, it should be. Except it would be nice to already use it like that. Radians. Okay, should like this. And then T sinus, NP sinus radians. Yeah. And then we place these elements in that matrix. It's again really easy. So cosinus, so T cosinus, cosinus, and deep learning will be able to learn these matrices itself. This method, which we will discover later. So sinus, T sinus, T cosinus, and then the last row is basically identity. So last row is identity, and this is the rotation matrix, and we'll see if this works. So I'm adding this to the slide number 16. If I run it, okay, it yet doesn't work. So we'll make it work. So I added this rotation matrix to the whiteboard. So let's look where this is used. So if I'm using rotation matrix, if I go to set angle, I see there is R, there is dot product, there is vector, but something doesn't work yet. Something doesn't work yet, I believe, because here is I think 0. Let's see again. Oh no, it doesn't work yet as well. Somewhere something is missing. We'll find what is missing. Oh right, this is because this is a vector. Update transformation. Oh right, here is not updated. So we need, okay, so in the static object update transformation, we will have multiple these matrices, these formulas, as I say, ready. For example, translation, which will be the movement around of the spaceship, and then we will have rotation as well here, right? So, and this should be applied to each of these nice vectors of the spaceship, and we'll show how to apply this to the vectors of the spaceship. So the way how to do this, so it's actually T here, right? So the easiest way, there is actually, it's applied here below draw library, but here if we change to R, it should work. So if I change to R, run, okay, now it's working. So we'll show you. So if I just change to R here, then it starts working. And this is deliberately with the C matrix. C matrix means combined all matrices together, or combined formula. And you will see that we will not do each matrix application like here, like rotation, translation, scaling, and so on by one to the vector, but we will do them all at once. This will be really cool. We'll be able to combine rotation with translation in just one 3x3 matrix. So that's that. Let's see. Okay, so here is the update. Transformation must have R there, and then it should work. I will show how it looks like. So slide number 17. So full screen. So if I'm rotating, it's rotating like this. By the way, you can see already some defects here. Defect number 1, you see around where it's rotating around the bottom part, see? So the way what would be nice if we could center it, that it rotates around the center. And how we do this is not by changing geometry, but we could add here another matrix operation that shifts it slightly and then rotates around it. I will show you how to do this. But is it working for you now? If something is not working, I will have to make sure that it works so far because we need to do the next thing as well.
I actually missed some part.
Okay, I can show you. So which part? Which part is
I don't have the triangle.
You don't have the triangle? Okay, let's go to the triangle part. So this is in the player. And the YouTube people, please write if you are able to replicate this so far. So here is the triangle in the player class. Okay. Kā tev izdodas? Okay. Jā, forši pamēģinām replicēt tik tālu, jo mums citādāk nav vērts iet uz priekšu, ja mēs neesam tikuši tik tālu. Tā. Look at YouTube. I see my friend there. Oh, nice. Like, honored that somebody that I know is also watching. Yeah. So this is that idea that we are using the matrix operations to draw the vector games, and the really cool stuff is that matrix operations for drawing games is exactly the same mathematics that used for deep learning, basically. We will see that in the following lectures. Okay, I can help you. So, kas tev nestrādā? Vai uzspied uz tā virsmu? Vai šitā pēdējās indīgas? Vai, ka tev tur nav iekšā ierakstīts rāda? Nu, tur funkcijā nav rāda iekšā. Tad mēģini uz priekšu vēlreiz, ja kaut kas nestrādā, es tev palīdzēšu. Kas tev nākamais vajadzīgs ir? Vai tev vajadzīgs? Šitās tētās strādā?
Nē.
Okay.
Tās nav īstais.
Ok, tad spiedi būtiņas, tad nekas nenotiek? Būtiņas. Tev strādā viss? Tev viss strādā. Tev savukārt nākamais, kas vēl varētu būt, ir parāda kodu. Tad uzbrauc augšā ar ieņemu, rotācijas matrici, uz pašai augšā. Jā, tas te ir paši. Tad meklējam, tur ir update transformation. Jā, uzspied kontroli virsū uz viņu. Jā, rekur te R ir aizvieto T vietā, rekur augšā. Šeit. Palaini vēlreiz palaist. Jā, viņš griežas. Okay. So the people in the classroom managed to get this far. This is great. And next we will do some other things. So I will add another task in the Moodle. And by the way, for the YouTube people, if anyone want to join the Moodle class, you should reach out. I will give the link. But this time working with those who are already in there. So the next task will be to move around the spaceship. And to move around the spaceship, so I think it's not surprising, we will again use the matrix, right? And this, as you say, in quote-unquote matrix formula. So I will share that one as well in a second. So this will be 2.4 task. 2.4 task. And it all says that we will need to combine the translation matrix into the variable C. So they combined, right? So I will show all of that in a second. It will not be difficult at all. And you will see the powerful properties of matrices. So let me add this to the Jamboard. No, not to the Moodle, I wanted to say. So the Moodle, new task, assignment, 2.4. 2.4, use the template for the translation. Check. Okay, so this is added. We'll show you how it looks like. So where is the okay, so here's the whiteboard. Actually need to rename it because it's annoying that I every time says the same thing. So rename, please get the task whiteboard. Okay, page 18 whiteboard. How it looks like. So I will just literally make a copy from Moodle so everybody sees it. So again, we will have a nice formula. and this will be this. So see, here we have a translation matrix. Please implement this in the code. I believe it's super easy for you. You already did this for rotation. Now need to do the same for translation. And here the trick is, again, why it's three-dimensional, not two-dimensional, even though we're working just with these 2 dimensions, is because we are rotating around z-axis. And for x and y-axis, we can also construct this kind of rotation matrix. It will look a little bit different. And here the what means the t here? So this means the delta translation by y-axis and delta translation by x-axis. And in this case, what we're looking at is translation along the, I believe, z-axis. So if we look at this would be z, then there is y and x. So this is, let's say, x and y. And we want to translate stuff around this part, not in some kind of three-dimensional space. Actually, using the same operations, what we could do, we could start building 3D games, but 3D games would be complicated at this moment. So if we have this nice triangle, for example, and if we would apply some, let's say, if we would apply some translation, please start to code this. This is not difficult. You need to do this in translation matrix function, right? And then I will show the C stuff. This will not be difficult. So if I say move 3 meters to the right and move let's say 2 meters down, and this will be relative from the current position, not absolute. So it's always, all of the matrix operations are relative, and this is really cool because then we can move stuff around and then rotate and then move again. So this will be really cool. So here, if let's say it will look something like this. So if I move it 3 units left, 3 units right, and 2 units down, it maybe will appear here. So it will be 1, 2, 3, and 1, 2 down. So this is what we want to achieve. Hopefully that's clear. Yeah, hopefully that's clear. Okay, now I'm moving back to the code, and we'll try to help you out. I really hope that YouTube people is also trying to fix this. Oh, triangle. Also, okay, those of you, wait a second. Okay, great. Thank you for comments. So some people reported that you had problem with rotating in strange order. Maybe it's because you have not here in this vector to 3D 1 at the end. So basically this extra dimension should have 1 there, because if you're working with the z-axis, the 0 will mess up a little bit the calculations. But so this could be one reason why it's malfunctioning. And also these functions I will add later to the home, probably because we will not have too much time to change them using matrix operations. Now they are just using the simple programming, you know, just selecting index 0, index 1, and adding 1. But you could do the same operation using the identity matrix multiplication. But remember, identity matrix can also change the size of the vector if it's a little bit skimmed off. I will show that later, but don't worry about it. So maybe add here 1 if it's missing. Maybe I can add this just for the sake of safety. And then I will show how to make the ship fly around, and then we can add some more cool features. So this is 18. Let's go to 19 page. Okay. So let's add here the translation matrix array. Again, the same thing as in top for the rotation matrix, just minor changes, really nothing difficult there. So 1, and by the way, these will be changed to floating points. If I add like that, then it will be floating, but it really doesn't matter at this point. So dx, and then the next one will be if you notice, it's again the identity matrix just added with some numbers like that. Okay, cool. So this is translation matrix. Again, this is this hard-coded formula to achieve certain projections or transformations. That's why they are called transformation matrix, on transformation matrices, yeah. It can be translation, it can be rotation, it can be scaling, it can be all sorts of really interesting ways how to change the locations of vectors or data points, if you will. So this is this. Then how to use it? We need to go to static object and then update transformation. Update transformation is the main function where we use all of this stuff. So if you would like to hack stuff, so don't write this, I will just show you. We could actually do here, where we go through each vector element, we could write here, do rotation, do translation. This will also be kind of okay, but not really. So, but because this is not optimal, so if I do this way, this will work, but I'm repeating dot product many times. See, like every time, like if I have very complex object, for example, 3-dimensional, like a robot or something, I will have to do this millions of times, right? So this is not good. So the best way, and this is actually the way how also deep learning works, is we need to pre-compute the total combined translation matrix beforehand, and then apply the same translation matrix for transformation matrix for each of the vectors in our geometry, and we can do it here. And also you see there is written order is important. If you do this in the wrong order, they will start to do strange things. We can actually play around with the order as well. So let's see. So how I advise to do this? Let's start it with identity matrix, identity 3. So, and then we do the chain together these things. So what we want to do, we want to first rotate MP, or let's say dot product between self rotate and self chain. And then we want to translate. And this way you can just add any kind of operation you want. Every time you add this, this will just be combined here. So one thing which I advise you is we could add here before this one, which I don't have it here, but you could add it, is this center. So make it center in the center of the, so that it's not rotating around the bottom part of the spaceship. But let's try how this works. So I will try to run it. Okay, it works for me. I will show it how it looks like. So really, with very, very simple changes, we can achieve huge differences in the way how this visually looks like, and the same thing goes about the data and the AI stuff. So let's see. So if I'm now rotating, it rotates, and now if I press arrow ahead, it will give a speed. So speed. See, it's already starting to fly. So I can fly around with this spaceship, and hopefully you can do as well. See, very nicely. Try to do this. Is it working for you? If not, I will help. So with escape, you can go out. And then basically what you can do more. So with this T centered, so here's the T center as well. So we could actually calculate this T center as well. So basically we can change the place where it's rotating. So if I'm running again, if I'm center, it's rotating around the bottom edge. And by the way, it's a little bit deformed because it's not the right aspect ratio. Now it's better. So it's rotating around the bottom edge. But if I would like to rotate it around the middle part, so I could calculate something like this: self T center, translation matrix, and then I want to shift it a little bit. So let's shift it not along x-axis, but around y-axis, so minus 0.5. And if I run it again, I believe we should have a better result. So now it's rotating around the middle of the circle, of the triangle. See? Now it looks much more natural, at least for the way how the game works, not with the bottom part. So the center of the mass now is in the middle, and if I'm running, it still works, see? So it's really cool. And if you change the order around, then bad stuff starts to happen. If I'm, for example, changing the rotation with the translation, then what will happen is that I will first rotate the whole rod and then translate, and this will not be good. So let's see. So now this works, and if I start to fly, then it starts to behave in really strange ways. So if I'm, it goes somewhere else. So this is the key knowledge that basically with matrix operations you can combine all of these great features into single 3x3 matrix here. So basically at the end this is 3x3 matrix, which applied to each of these vectors achieve the whole different behavior. So did you manage to run this? I will go around and check. So if I'm, I've also put this in the whiteboard. Just a second. So this is really fantastic what you can do with linear algebra and matrix operations. Next time, by the way, I will have another visual example. We will try to make a robot arm, and we will use the linear algebra together with calculus or augstāko matemātika, partial derivatives. And partial derivatives together with these matrices you can do even great, more cooler things. So, just to palīdzēt kaut kā sakt. Okay, tā pamēģināt palaist. Jā. Jā, spēr. Uz augšu iet tur. To speed position mainās uz pēc escapes un izklausās izskatās pēc ingrus lietas. Uzbrauc augšā tur, kur ir tas vektor 3D zemāk. Zemāk. Reku šeit ielēc viennieku. Tagad to strādās. Kā tev izdevās? Uzspiež uz augšu pultiem. Jā, tas ir forši. Un tas izstrādā. Ok, rekur, Nils, vai ne? Nilam strādā?
Man tā neiet uz augšu.
Es uzspēju skrietnīm augšā redzās position mainās, redzat?
Jā.
Tas nozīmē, ka position mainās, bet kaut kas cits nemainās. Kur ir tā translation matrix? Rekur, dx, dy, izskatās labi. Aizbrauc uz to update transformation parāda. Zemāk, jā, rekur, C, translate, izskatās, arī, kur tev problēma, tev T center jābūt. Okay, cool. For people in the live audience, it managed to work. So this is fantastic. Let's look at some last examples and then we'll wrap up for today. And then in the home, using the same techniques, you can make it so cool game. You can add, let's say, asteroid. So asteroid, it's easy to add. You just have some kind of, I will give you a formula where you add points around like a circle, right? And then you can use the circle as an asteroid, and you can distort it with randomness a little bit, so it's not rigid. So it's really cool things you can do. So, but again, this the same. So you will have opportunity to implement, let's say, skewing matrix, for example. Let me see what else do I have here. So riņķa līnija, that circle, that will be something. Okay, actually, let me show you, because we don't running out of the time, the things which you can do more here, and I will give some tasks. Right. Okay, let's do one together. So here, this part. So now this is programmatically changing 2D vector into 3D vector. We can do also this just using matrix operations, which is even cooler. And this is something just to keep illustrating how powerful are the matrix operations. So for example, 2D to 3D. So let's do this together. So here, E, this will be the identity matrix. We can write it manually as well. And this will be not like a full identity matrix, but like a little bit skimmed off, because the full would be with 3 by 3. So 0. And I will just use this identity matrix to achieve the same thing as this line. So the same thing as this line, where we change from 3D to 2D just using the matrix multiplication. So here would be vec 3, And if everything is right, the behavior will not change for the game. So dot e comma vec2 plus, and then plus it's because there is this 1 at the end, np array. I'm just wanting to illustrate that using the matrix operations, you can do the same things as with the manual programming with selecting elements. So that's that. And the other part is even cooler here. The 3D to 1D, 3D to 2D, it is just one dot product and nothing else. So because when you add some dimensions, it's a little bit more. So like this. 1 0 0 0 1 0, and then the dot product vec 2d equals dot e vec 3. That's it. So this is also a great illustration how using the property of the dimensionality. So for example, in this case we have, let me show you. So in this case we have the shape of 3 by 2, and the input shape is of course 2, right? And the output shape now is the 3. So, and what we did, we projected in higher dimensions. This is also something very cool that needs to be understood. With matrix operations, we not only can do what I said, like a shadow of object. I have, let's say, this object in front of me, and if I have a shadow of light and then it is on the table like a square, we could also do the opposite way. We can have the shadow on the table and project 3D object out of it. It's actually doable with these techniques. That is one of the reasons why deep learning, these generative models, can do crazy things. They can literally produce, you put in the model to the picture, for example, and then it comes out the 3D model. This is possible to do nowadays. And we can build these models later together if you want. But basically, this is power of matrix operations. And also here, from the true 3 dimensions to 2 dimensions, I have coming in here the 3 dimension. And if I create the correct order here, yeah, 2 by 3, I get out 2 dimensions. So this is very cool. So if this is correctly implemented, it should not change the behavior of the game, and it does not change for me. If it changes for you, I can help you. And let me show a couple of last things, and then we'll wrap up, and then you will have some interesting tasks to do home, and we can later check them together, because all of these things are important to understand in order to achieve at the end that you will be able to basically do proper research in deep learning and so on. So basically what happens here? If we want to add the skew matrix, so the skew matrix means that it will be like, let's say, squished, right? Or something like scale matrix, also the squished, right? So we would add some new matrix somewhere in between this chain, right? And it will achieve the result that something is squished. So that's that. Then the planet. Here is the generate geometry, and how we could generate geometry for the planet. Just a quick glance how we could do this is, so we could have some kind of theta. You can write that as well. So the theta while theta. I will add the formula later in the Moodle. So while it's while it's 2 times np, so this is the full circle, right? And then we will add some theta step, theta plus step, and the step will be, let's say, some kind of value here. For example, what could be step? So so this will be in radians to np, and let's say 20 dots along the line. And then you would calculate literally the x and y values based on the angle. So you will go angle around the circle and add these values to the geometry here. Append here, right? So this will be the task to create the planet. And basically when you create the planet, then here below if we go down, you see in the game, we add here player and 2 planets, see? We also add asteroids here, 5 asteroids. So if you implement the correct geometries, they will suddenly appear and start flying around. Basically, that's about as simple as that. I will give you the formulas how to do this later, and you just need to add in these few little places couple of lines of code, and your game will be ready to go. So that is the plan for the home. And next time we will look at what games we managed to do. You can extend game, even add the gravity. It's not necessary, but you can add gravity, you can add rockets and so on. And next time we will look at the robot arms. So robot arms implemented using the same mathematics. You will have robot arm, and it will say, go and pick this object up, and you can calculate it geometrically, or you can calculate it using the calculus and linear algebra. And this will look super natural how the robot arms behave, because all of this mathematics is all around us in the world, and now it's becoming like useful in reality. Okay, good. I really hope that this was informative, useful, and so on. And the one thing which I need to mention at the end today is that okay, those people who have still problem with 3D rotations and so on, I suppose you could send me email with the code, and I can assist you. So let me give you my email. So at RTULB. So here, yeah. So you can send me that, and I can assist you fix this, and then you can continue working on the homeworks. And the one thing which I must mention is the next week I have again conference. So this is something I really try to work around, but there is no way that I can be always at the same time. So my suggestion is that we can do this lecture. Actually, we could do this lecture in person here in Ventspils on 4 o'clock on Wednesday. Is it possible or not possible for you?
Wednesday?
Yeah. No, not possible. Remotely?
Remotely?
Yeah. So let's try to do then remotely Wednesday on 4 o'clock, and then a week after again we will change the sometimes Chetros. You cannot, yeah. You have another lecture, and then okay, let me I'll give you some other opportunities. So what about
It's recorded, right?
yeah, but no worries. Let's try to do that. We have as many online people as possible. So let's say in person in Ventspils and on live on Tuesday 6. Okay, Tuesday 6 live and in person here. Okay, if you're not in Ventspils. Okay, so you
Tuesday 6?
yeah, but again, this is just exemption. We'll usually not do this, but like in 99% of the time, like not 99, but let's say 90%, it will be Fridays. Sometimes I will go also to other locations. So, but anyway, so this is the plan now. So next week, Tuesday 6, we will have another lection, and hopefully, because again I have Riga conference. Okay, great. Thank you everybody for joining. Nice to see 6 likes. Hopefully you can survive this course, and yeah, let's meet next week. Okay, bye bye.